Again, this problem says, oops. This problem says the sun's mass is 2 times 10 to the 30 kgs. Its radius is 7 times 10 to the 5 kilometers, and it has a rotational period of approximately 28 days. If the sun should collapse into a white dwarf of radius 3.5 times 10 to the 3 kilometers, roughly by a factor of 200. And that's what that is, by a factor of 200. So your radius collapses, your moment of inertia decreases, and so your angular velocity will increase. What would its period be if no mass were ejected and a sphere of uniform density can model the sun both before and after collision? Okay, so in this collapse, just like a skater when she brings her arms in, omega final. So in this problem, what angular momentum is conserved? Initial angular momentum is final angular momentum. Okay, let's write that down. Okay, and so the moment of inertia decreases because the radius decreases, and the moment of inertia of a solid sphere is given by 2/5 mr squared. Okay, and so let's put all these in, and omega, by the way, is given by 2 pi divided by the period. Angular velocity is given by okay, so this is one revolution is 2 pi radians, and period, let's say in seconds, okay, is so this would be radians per second. All right, so let's calculate all the quantities. I initial is 1/2, oops, no, 2/5. The mass is 2 times 10 to the 30 kgs, and the radius is 7 into 10 to the 5 kilometers, but 10 to the 8 meters squared. So I initial works out to, and let's take your powers of 10, that's 10 to the 30, that's 16, 10 to the power 16, 10 to the 46. So that's 4 times 7, 28 divided by 5. Okay, so initial is 5.6 into, oh no, not 5.6, that's a 7 squared. So 49 into 4 divided by 5. 39.2. So 3.92 into 47, 10 to the power 47 kg meter squared. Similarly, I final is 2/5. The mass is the same, 10 to the 30 kg, except that the radius is now 3.5 into 10 to the power 6 meters squared. And that works out too. That works out to 9.8 into 630 10 to the power 42 kg meter squared. Okay, and that's I final. All right. Omega initial is 2 pi divided by radians divided by 28 days, and each day is 24 hours, and each hour is 3,600 seconds. So that's the initial angular velocity, 2 pi radians per seconds, that many seconds. So, and this is okay, so 1, 2, 5 into minus 5. So this works out to 2.6 into 10 minus 6 radians per second. Okay. All right. That's omega initial. So now we have everything to do omega final. So I initial omega initial equal to I final omega final. And what is it that we want? What would its period be? So what we want is the final period. So I initial omega initial equal to I final 2 pi T final, and okay, so T final is I final times 2 pi divided by I initial omega initial. Alright, so now let's put in these numbers. I final is 9.8 times 10 to the 42, 9.8 times 10 to the 42 kg meter square, 2 pi radians, and I initial is 3.92 into 10 to the 47, 3.92 into 10 to the 47 kg meter square, and what else? Omega initial. Omega initial is 2.6 into 10 to the minus 6 radians per second. Alright, so let's take care of the powers of 10. This is 47 minus 6 is 41, so that leaves, okay, let's make sure this is clear. This is 10 to the power 47. Okay, so this is 10 to the 41, that leaves 10, so this is equal to T final is 98 into 2 pi divided by 3.92 into 2.6 seconds. Okay, so let's this cancels with that, and the radians cancels, and the seconds come to the top. So the final period in seconds. Okay, and this is equal to okay, so 60 0.4 seconds. So the period of the sun, right now the rotation period of the sun is 28 days, and when it collapses into a white dwarf, its period will become 1 minute. Okay, so it'll be rotating quite a bit faster. All right, that finishes this problem.